In this video, we're going to work with both gradients and contours, and we're going to start right in with a function defined by x, y squared. And we'll start by defining the level sets or the contours of that curve. We're going to take a single point on there, so never hurts to sketch. We have our x direction and y direction. We're at the point 2, 1, so 2, 1. And there's going to be some contour through there. What contour is that? Well, at the point 2, 1, we're going to have f of 2, 1 equals 2 times 1 squared, which is equal to 2. So we are interested in the contour or the points at height f equals 2. All right, let's go track those down. So what we're going to do is set our height to 2, and then we'll use our function xy squared, and we're going to work with that to try to get some kind of graph that we can draw. Typically, how we draw graphs is by isolating for y, so let's do that. We'll have y squared equals 2 over x, or y equals the square root of 2 over x, and because our x's are positive, we would take the positive root of that. Without knowing any real details about that function, it certainly looks like it has the typical asymptote kind of feel, something like that. So that would be a sketch of the contour for this particular example. Next, let's bring in the gradient. We have our function, which was xy squared. The gradient is equal to simply the package of the x derivative and the y derivative. Well, that means we need to compute those two derivatives. Taking the x derivative gives us y squared. Taking the y derivative gives us 2xy. So the gradient vector in general at xy is literally this term, y squared, comma this term, 2xy, and the only thing we're adding now is at the point 2, 1, the gradient at the point 2, 1. Be careful with the x's and y's. This is a y value, so it's 1 squared, which is 1, and 2 times 2 times 1, which is 4. Okay, so we found the gradient vector at that point. Now we're going to change gears a little bit. Find an equation for the tangent line at 2, 1 to the contour through the point. All right, let's go back for a moment. We found the gradient vector here was like 1, 4. That was our gradient vector. Now we're asked to find the perpendicular line to that, but we're not going to assume that we know that yet. What we're going to do is simply find the tangent line to this formula. Now that formula is a bit awkward to find tangent lines. This is going back to the fall term. We're going to use this formula here and some implicit differentiation, which will be easier to work with than the nasty square root stuff here. So what we have is a curve defined by 2 equals xy squared. This is going to be a full, regular, single variable, linear approximation or tangent line. And that's equal to, or given by y equals a slope times x minus a plus b, or actually plus c, or y naught is probably the best choice there. We already know actually what these values are. We're doing this relative to x equals 2 and y equals 1. The only thing that we're missing here is a slope, and this, careful, is an x or a y versus x slope. And if that's the case, and we have a formula like this from the fall term, we would use implicit differentiation to get dy dx, which is a slope of y with respect to x on that diagram, on the xy plane. All right, so we're bringing back some good stuff here. We take the derivative of both sides with respect to x, xy squared, now treating y as a function of x, so it's a very different field than this because we're approaching the calculation in a different way. We're imagining we've got a red line as our curve, and we're trying to find the relationship between x and y. If that's the case here, we get 0, and the x derivative, this would involve a product rule for this calculation, we're going to have 1 times y squared plus x times 2y dy dx. And that's what we're interested in computing here. If we isolate for that, we're going to have dy dx equals negative y squared divided by 2xy. And if we tidy that up, we'll have negative y over 2x. At the point 2, 1, that's going to equal 1 over 2 times 2 is 4 with a negative out front. And so we bring all this together. I'm going to erase these ingredients now. We can put our negative 1/4 in for that part. We'll place these values here, and that is the formula for our tangent line to the contour. If we were to draw a straight line, this blue line here, it would be defined by y equals negative 1/4 x minus 2 plus 1. All right, we now have a line, we have our gradient vector. With all that extra information, let's draw a more detailed diagram. We have the point 2, 1, and we have a slope of negative 1/4, which pushes us out to there and there. That would be our tangent line. We also had the vector 1, 4. Well, that would be 1 over and 4 up. So if we were to draw that, it would look like this. That was our gradient vector at the point 2, 1. And as we indicated earlier, we had the actual contour, which was defined by y equals the positive root of 2 over x, and that would be some kind of asymptotic graph. But by the time we get down to this point here, it has to be tangent. And away we go, and it would not ever cross this line here. So what we'd see is actually in this diagram, that perpendicular nature. The slope of this line is negative 1/4. The rise over run of this vector is 4 to 1. And so we do get perfectly perpendicular lines out of these calculations, reinforcing that relationship between the gradient and the contour lines. For reference, here's a more detailed contour diagram of that function again. Now we can see that this is the uphill direction, reinforcing that the gradient points in an uphill direction and not the downhill direction. And as we indicated, we would have something perpendicular to the contours. Try that again. There we go. So that, being our gradient vector, matches our earlier calculations. As a wrap up for this collection of videos, there's an important distinction, and it's easy to get confused because of the two new concepts that were introduced almost at the same time. One concept is the directional derivative, and the other related one is the gradient. So if you can keep their purposes and their meanings distinct in your mind, it'll make life a lot easier. This du f of ab is a very specific quantity, and the key thing is it is a scalar number. It is a slope. You tell me I'm at this point AB, and I'm going to move in some direction, u, and I have the surface over top. This du of f of ab is the slope of the surface in the direction surface in the direction of u. So if we say the slope is 5, that makes sense. If we say the slope is a vector 2, 7, that would be very strange, very weird, and wouldn't make grammatical or physical sense. So keep in mind that at the end of the day, the slope should be a number. The gradient of f at a point is a vector. So we pick a point, AB, we have our surface. If we do the calculation, which is gradient of f is equal to the x derivative comma the y derivative, we just get a vector. Could be anything. No magnitude restrictions, no direction restrictions, could be anything. That direction, though, tells us something important. That direction is the direction of maximum increase. It's not the slope by itself. It tells us in this direction we will find the steepest slope. The magnitude of it would be how steep the slope is, But the first thing to remember, the most important thing to remember, is that this direction is going to point us uphill in the fastest step, or the most steep direction. So it's an answer to the question of, hey, I'm at a point, what way should I go? What direction should I go to go uphill, to stay flat, to go downhill? Those are all direction questions, and so the answer has to be a vector. And notice the gradient is in fact a vector. It's the answer to the steepest uphill direction. So the two quantities here are related. This directional derivative is calculated with the use of the gradient as a step along the way, but one is what is the slope in a direction that I pick, and this other question is what direction should I go to get the steepest slope. If you can work through that through the practice problems and separate those two ideas, it'll make a lot of sense.